Hello everyone, and today I'm going to prove the irrationality of the square root of 2. So we have the theorem that the square root of 2 is irrational. So we are going to prove it by contradiction. So we suppose that the statement is not true and that the square root of 2 is rational. Now, by definition of rational numbers, that means that it can be expressed as a ratio of two integer numbers, p and q. Notice that we can assume that p and q are coprime, because if they are not coprime, then we can divide both of them by their greatest common divisor. And notice that when we divide both the numerator and denominator of fraction, the value of the fraction remains the same. So when we divide by the greatest common divisor, the value remains the same and the numerator and denominator become coprime. But what we, in particular, what we need from this is that p and q are not both even at the same time. So if they're even, then they're both divisible by 2, which means that they're not coprime. So they are not even both at the same time, which means that either only one of them is even and the other one is odd, or both of them are odd. So now let's rewrite the expression that we have. So the square root of 2 is equal to p over q. From this, when we square both sides, we get that 2 is equal to p squared over q squared. Now we multiply both sides by q squared. We get that 2q squared is equal to p squared. And from this we conclude that p squared is even. So now let's prove a lemma. So for any integer x, if x squared is even, then x is even as well. So we are going to prove it by contradiction. So suppose that x is not even, which means that it's odd. So if it's odd, then it can be expressed as 2m plus 1 for some integer m. Then x squared is equal to 2m plus 1 squared. And then this we can rewrite as 4m squared plus 4m plus 1. And this in turn we can rewrite as 2 multiplied by 2m squared plus 2m, and all of this plus 1. So this means that x squared is odd because it is expressed as 2 multiplied by some integer number plus 1. So it means that it's odd, which is a contradiction. So now let's return to the original theorem and its proof. So we have that 2q squared is equal to p squared, which means that p squared is even. So by the lemma we get that p is even. Now it means that p can be expressed as 2m for some integer m. When we rewrite the expression 2q squared using this, we get that 2q squared is equal to m all squared, and this is equal to 4m squared. So it means that q squared is equal to 2m squared, like we divided both sides by 2. So, but this means that q squared is even. And now we can apply again the lemma and get that q is even. And this means that both p and q are even, and this is a contradiction with our earlier assumption that p and q are coprime. So this concludes the proof.